All right, we're in section 2.2. We just organized our qualitative data, and now we're going to be organizing quantitative data. Remember, quantitative data has to do with numbers. So if you want to just write yourself a little note, quantitative means numbers, quantitative versus qualitative, which is a quality, numbers. Okay, so it's going to be really similar at first, but one of the things that's different, the categories of our data now are going to be called classes. So we have our first kind of definition. Before, the values of the variable for qualitative was called categories. For quantitative variables, the value is going to be organized into classes. And remember, when we talk about quantitative data, we have two different types. So we're going to be doing two different techniques. We have our discrete, and we're going to be talking about that first. And discrete is countable. So 0, 1, 2, 3, 4, 5, etc., etc. Or just a finite amount. You can think of that as well. So then in this case, the classes, the values of how we're organizing our data, the classes will just be the observations. Classes are observations. And the other type of quantitative data we have is continuous. And remember, these are finitely many values, a measurement of some sort. So this is a measurement. We can always get more and more and more and more precise. We have infinitely many values. So in this case, our classes will be intervals. Because we have infinitely many values. So if we had infinitely many classes, our data would be useless. All right, so we're going to start talking about the discrete first. So here's our first example, again for discrete data. The following data represent the number of available cars in a household based on a random sample of 50 households. We're going to construct a frequency and relative frequency distribution. So far, this is almost exactly what we saw in section 2.1. The only thing that's different is the value of our variable are going to be numbers. So let's break this down. So again, we do a tally, much like we did before. So for instance, this is our raw data. With raw data, we start our tally chart. 0 cars in that household, 1 car in that household, 2 cars in that household. All right, and again, they've already done all this for us. And once we're all done organizing our quantitative data, we can figure out the frequency. Once we do the frequency and we have our total number of observations, in this case we had 50 households, we know that. We can create our relative frequency by looking at parts to the whole. So parts to the whole. So 4 cars out of 50, that's the relative frequency. 13 out of 50 households, had 1 car. 22 out of 50 households had 2 cars. So that's how we're getting our relative frequency, just like we were doing before. All right, and so we know that the relative frequency adds up to 1. And a couple other things. The values used to be called categories, but now they're called classes. And then the number of cars, this is our variable. So just breaking down our frequency chart. So really similar. So now this is where it's going to change a little bit. Just like with our qualitative variable, once we had our frequency distribution and relative distribution, we created tables and graphs, right? We created our bar graph or our pie chart. We're going to create something similar to a bar graph from our frequency distribution, but now that we're working with numbers, it's going to be called a histogram. And a histogram is essentially a bar graph, but the bars are touching. And that's really the only difference. Let's check out the definition. It's constructed by drawing rectangles for each class of data. The height of the rectangle is the frequency or relative frequency of the class. The width of each rectangle is the same. And the rectangles touch each other. And this is going to be something I look for. If I ask you guys to draw a histogram, I want to make sure there's no space in between the bars. Because a histogram, the bars do not touch. All right, and again, same thing with our histogram as the bar graph. The frequency and relative frequency, if it's coming from the same set of data, the bars are in proportion to each other. So we're going to get the same distribution. So these are the same, even though one is a relative frequency and the other one is just a frequency. All right. And again, we have our classes, so we can write that. Just some notes for ourselves when we're constructing our histograms. All right, and then in some examples too, you'll see that people will write the actual number above the rectangle, just because sometimes it's kind of hard to tell otherwise. And then you guys can do that in your quiz too, just to make it extra clear, because I know we like to be very, very clear on our quizzes. We want to communicate as clearly as possible. All right, so discrete data, countable, really straightforward as far as it being very similar to the bar graph in section 2.1. So now we're going to look at kind of a harder case, and harder just in the sense of how we're going to organize our classes. So for instance, let's consider this. What about discrete data that has many values, or continuous data that has infinitely many possible values? Well, we've already talked about it. We're going to create classes using intervals of numbers. Create classes using intervals of numbers. And to highlight this, we're going to look at age. All right, and we see that sometimes we're filling out a form and we have to check off an age bracket. Age bracket is an interval of numbers. So we're in this case where age is a quantitative variable and it's a measurement of how long you've lived. So it's continuous. Okay, so because it's a quantitative continuous variable, we know that the classes are intervals. And we have units too, so that's intervals in years. Okay, so some examples of this, it might look like, so we would say this is in years. And I'm going to create the classes right here. We could look at something like 25 to 34. So if you're somewhere between the ages of 25 and 34, you would belong in this class. And then so we don't skip any ages, our next class would start at 35. And let's say we go 35 to 44 years old. And so our next class should start at 45, etc., etc. How high are we going to go? Well, let's do a couple more. And then we'll hit the retirement age. And we'll just go 65 and up. So age, quantitative continuous, our classes are intervals. Okay, so let's use this to define some things, right? Let's use an example to define. The first thing we're going to talk about, let's just take one example. We'll take 35 to 44. All right, that first number 35 is called the lower class limit. It's the smallest value. It's the smallest value in that class. All right, so that's your 35. And then we have that 44. If this one's called the lower class limit, 44 is the upper class limit. And it's the biggest value in that class. All right, and again, it's a continuous variable, so really it's anything less than 45. So you can be like 44 and a half, 44 and 3/4, etc. So this is the biggest value in class. All right, what else can we define? So we can also notice that as we progress to each class, we're increasing by 10. So that 10 is called the class width. And how do we calculate it? We calculate it vertically. So it's the difference between consecutive lower class limits. The difference between consecutive lower class limits. So for instance, consecutive lower class limits, it's 25 and 35. And that difference is 10. And then going from 35 to 45, again, that's 10. So 10 years is the class width. 10 years is the class width. Common mistake is to calculate the class width within a class. So for instance, the incorrect answer would be 9 years. People will go 34 minus 25 is 9. But it's not. We do it vertically. We calculate the class width vertically. So 10, 10, 10, 10. The class width is 10. Okay, so, and finally, one last thing with this example. When we have this, when there's no upper class limit, we just say that it's open-ended. Ooh, lots of definitions for this very simple example. Okay, so of course we're going to ask ourselves, how do we construct these classes? How do we construct the classes? Why did I choose the starting point to be 25? Why did I choose the ending point to be 65? Why did I choose the class width to be 10? All right, so there's no right answers. Sometimes you just have to fool around with the number of classes until you figure out the classes that best represent data. In general, we want between 5 and 20 classes. And this, how you decide if you should choose 5 or 20 is going to be based on how big your sample is. If you have a small sample, maybe you'll just have 5 classes. If you have a very large sample, you can have up to 20 classes. Something else, too, is the spread of data. If your data is really, really close together, all the numbers are close together, maybe you want more classes to kind of break that up so you can see trends. If it's far apart, maybe you want fewer classes so you can see some trends. All right, and then once you know how many classes you want, we have to figure out the class width. And to do the class width, we have a little formula, and we'll practice this later. You take your largest value in the data set minus the smallest value so that's going to be a type of range, the range of your data, how much it varies, and you're going to divide that by the number of classes you want. And that's going to tell you what your class width should be. All right, so there you go. And again, we're going to practice that more in your homework, and we're going to practice that in an activity as well. We're going to look at one more display of quantitative data for this section. It's called a stem and leaf plot. All right, and so here's the philosophy. When we group data into intervals, we lose the raw data. So for instance, let's go back to our example with the ages. If this was our class, these are classes, and we start grouping the data in here, well, let's say we had a 27-year-old, a 32-year-old, a 26-year-old, and a 30-year-old. So we would say there's 4 people in this first class. But then, when we just see the result, we lose the raw data. If we just say there's 4 individuals in this class, we don't know how old they actually are. So when we group classes when we group data into classes with intervals, we lose the raw data. The stem and leaf plot fixes that. So the stem and leaf plot gives us a visual without losing the raw data. So let's do it with this following data. So this is just some generic quantitative values. And we're going to demonstrate how to do a stem and leaf plot. So a stem and leaf plot uses digits to the left of the rightmost digit to form the stem. And each rightmost digit forms a leaf. All right, so let's look at the leaves first. It's the rightmost digit. Whoops, I was just 2, 0, 3, 7. Good. So those are all our leaves. Our stems are going to be the 28, another 28, 28, 29, 30, 30, and 28. Okay, so for instance, let's look at this 28. We'll do a cute little visual. 28 would be the stem. And then off the stem, we could have 10 leaves. We could have 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. Okay, so this stem could represent or could account for 10 different numbers. So how is that going to look in our stem and leaf plot? Okay, so our stem and leaf plot begins with a line down the middle, and this is going to separate the stems from the leaf. All right, let's go up a little bit. Don't lose the data. All right, so on this side it's going to be the stem, and then it'll be the leaves on the right, just like the actual number. And if we go back to our data, our stems are 28, 29, and 30. So we can write 28, 29, and 30. And now let's talk about our leaves. So let's just go through the data, and we'll do our leaves in blue or green. So our first leaf is 9 with stem 28. So we're going to go to the stem 28, and we're going to write the leaf 9. All right. And now let's go to the next one. So stem 28, leaf is 7. Stem 28, leaf is 2. Stem 29 with a leaf of 6. Stem 30 with a leaf 0. 303. And then finally another 287. We have to write it again though, because we have 4 values in this stem. So we're allowed to write it twice, and we have to write it twice. Okay, so this is our stem and leaf plot. We are all done. And notice we do get a distribution, but we do not lose the raw data. So we can easily turn this into a histogram. There we go. Whoops, like this. So we can get the distribution shape, the shape of the distribution, but we can go back and we can figure out all of the data. The only thing though is we need to include a legend, because we don't know if this is 28.9, if it's 28.7, etc., etc. So we would include a legend, and it's something I look for when I'm asking you guys to do stem and leaf plots as a quiz or the exam. You guys have to have a legend, so you can just come in here and say that when I have this on my graph, it's not 29.6, it's not 0.296, it means 296. And with this legend, we can figure out all of our raw data. And it's also, again, really similar to our other histograms. For instance, let's look at this first stem. This stem actually represents a class the smallest value in the class, let's see, the smallest leaf value would be 0. And the biggest leaf value would be 9. So this represents class 280 to 289. And likewise, this stem of 29, the smallest leaf is 0, and the biggest leaf is 9. So it represents an interval of numbers again. And we also have a class width. What is that class width? For this particular setup, the class width is 10. All right. So good. So we have 2 nice visual displays of quantitative data, our histogram and stem and leaf plot. Now that we can have visual displays of data, we can start talking about the shape of the distribution. And this is going to be very important to us. So we have 3 different shapes that we have to memorize. The uniform distribution means that it's just a box. All of the values are the same. All the values in your classes are the same. So the uniform distribution, it's spread evenly across. Bell-shaped means we're looking at a distribution that's shaped like a bell. So the biggest values are in the center, and it just kind of decreases. And sometimes this will be approximate. It's very rare to have a perfectly bell-shaped distribution. So let's keep that in mind when we're trying to judge what kind of distribution. Skewed right means we have a long right tail. So skewed right, I'll do that in a different color. Skewed right means we have a long right tail. Versus skewed left means we have a long left tail. So when we're talking about skewed, we're talking about the tails. We're talking about the tails. All right, so now we have ways to have visual displays of our data, and we also have words to describe our distribution. We also have vocabulary terms to describe our distribution. So these are definitely going to go onto your flashcards.